reasoning ought to be, and then mention certain other things along the way. You should be able to find this in the live stream as well, right? So it should be accessible there. So we're going to start off with, sorry, Saram.
No, sir, thank you so much.
Okay.
It's fine. We can start.
Okay. Okay. All right. So what we want to start with is some reaction kinetics first, and not in the sense of, again, a topic that consistently comes up is when we are writing, again, equations for multiple stages of a mechanism, right? So here you've got fluorine reacting with chlorine dioxide, ClO2 as shown. You've got F2 plus 2 moles of ClO2 give 2 moles of FClO2. Now, one other point that's important to make here, remember, all of these molar coefficients that you see in the equations, completely independent of the rate equation itself. That's the first thing that needs to be said before we do anything else in regards to what we're seeing here. Because it's often one of the biggest mistakes that students make is that they automatically assume that these coefficients pertain to orders of reactions, and they absolutely do not. Now it says that the rate of order is the rate of the reaction is first order with respect to the concentration of fluorine, and first order with respect to the concentration of ClO2. Now, generally, when they do something like this, the moment that they tell you this specific point, that it is first order with respect to both of your reagents, you can see in the equation that there's 2 moles of ClO2, but that means that in your rate determining step, you should only have 1 mole of fluorine and 1 mole of ClO2. And since you couldn't do that if you wanted to in the second step of the mechanism, that's their way of specifically telling you that the first step is your rate determining step itself. So, for example, because it's first order in both, that means my first equation will be F2 plus ClO2. And now the next point of understanding, what do we do with this? Is this sufficient as a formula itself to justify what would end up forming at the end? Intermediates can pretty much be anything that is a reasonable particle within an actual chemical reaction. What that means is that in the mark scheme, they show this thing. And let's talk about why this thing could form at all. The process behind it is, remember that chlorine is an element on the third period forward. And any element that's in the third period forward has the ability to make more than, or has the ability to expand its octet because of the empty d orbitals that it contains. So this is why chlorine is able to make that additional bond to the fluorine atom, creating this particular particle. And in turn, it leaves a fluorine free radical behind as a result. So now you've got one fluorine free radical in this point in the actual mechanism. Your fluorine free radical, it's my intermediate. I know that it cannot be there at the end of the reaction. So somehow in the next step, it has to be used up. So we take that same fluorine, we react it with the remaining mole of ClO2, and we get 1 more mole of FClO2. This is how I reasoned out the breaking down of this mechanism. No other particular purpose other than the fact that I knew that chlorine could expand its octet. Chlorine could make that additional bond beyond its one bond that it was making with the one of the oxygens here prior. And so I had it actually bond on to the Cl. I had a fluorine left behind as an intermediate, and then I had that fluorine bond to the remaining ClO2 to give me my second mole of my product. Now, if I ever want to check my reaction, what you're supposed to do is simply compare what you've done, cancel out your intermediate. So this would cancel out, this would cancel out. You can see that in your overall equation, there would be 1 mole of F2, there would be 2 moles of ClO2, and there would be 2 moles of FClO2. So it's exactly equivalent to the equation that you've written, right? As you've presented it, as you've shown it, right? And you've also specifically focused on the understanding that, again, using the order in the respect of what we saw with the first order with respect to fluorine and ClO2, you've shown that in your first step as well. Now, the second part, when it said this, as we said at the beginning, it had already told you that step number 1 is my rate determining step. And the reason why it's a rate determining step, as there are, or as there is 1 mole of F2 and 1 mole of ClO2 in this step of the mechanism. That is the idea that we want. That's the understanding that should be there in our understanding before we want to move on ahead to making any other suggestions. All right. Now, next part is pretty straightforward. At this point, I wasn't really concerned with the B parts of this particular question because they're pretty self-explanatory. They go into the rate equation. So when the rate of the reaction is measured in moles per dm cubed per second, the numerical value of the rate constant K is 1.22 under certain conditions. You've been asked to, again, complete the rate equation for this, stating the overall order. So the rate equation would be equal to, let's start with that part first, K times the concentration of F2 times the concentration of ClO2. That would become your rate equation. And if you look at it in very careful understanding, there's 1 mole of F2 or one first order for fluorine, first order for Cl2. You would have 2 as the overall order of reaction. All right? That's the understanding that we want. Now, it is also imperative that you remember one other thing. When you know what the overall order of the reaction is, you can go ahead and predict the unit for K in this equation as well, right? So for example, if I want to know what the unit for K is, since the reaction is overall, again, second order, the unit for K would be mole minus 1 dm cubed S minus 1. If you'll hang on 1 second. All right, now moving on to part 2. Using your rate equation in part 1 to calculate the rate of the reaction when the concentrations of F2 and Cl2 are both 2 times 10 to the negative third mole per dm cubed. So again, this time they've told you what the K value is. They've told you what the actual concentrations are. Simply plugging into your calculator is the only thing that you need to do. Your rate should come out to be 4.88 times 10 to the negative third. Sorry, I had done the calculation a little bit earlier, so instead of doing it here and writing it out, I've gone, just to save us some time, I'm going to go ahead and write the answer here in terms of what we have and what we know, right? So once again, you get 4.88 times 10 to the negative 6 will be your actual value. And again, what we did here was we took our three expressions, the 1.22 and our concentration, or concentrations, I should say, and we simply multiplied them together. That's how we end up getting this numerical value. All right. Now, again, C part under different conditions in the presence of a large excess of ClO2. Now, it's told you that the ClO2 is in a large excess. That means that the rate equation is as shown. You can see that the overall order has now become first order. And you need to remember this, that this particular understanding we're going to talk about in just a moment here. It says that the rate equation is now K1 times the concentration of F2. Half-life of the concentration of F2 is now 4 seconds under these specific conditions. Now, what do we need to do to solve this particular part? I want you to calculate the numerical value of K1 giving its units, and the way that we want you to determine the value of K is using this specific formula. Now, what this is doing is it's taking actually the ln value of the temperature and working it out in terms of the energy of the particles. Now, I tell my students, again, the derivation is not important as much as it is your ability to understand. So whenever the overall order of your reaction is first order, then you can actually find the value of K by setting up this expression, which, and by the way, this 4, by the way, in the formula should be half-life. I apologize, but this is what we want you to remember. So 0.693 over your half-life will give you your expression for K. Whenever, again, the overall order for the reaction is first order. So again, just not waste the time and get to exactly what we want here. The value comes out to be 1.73 times 10 to the minus 1, right? Or you can write 0.173 down as your answer. Now, for the unit part, again, this time the overall reaction was first order. So whenever the overall reaction is first order, then all you're going to do here in terms of your formula or your unit, the unit for K would always be S minus 1 because mole per dm cubed would cancel, excuse me, alhamdulillah, out from the process. Now, part two, an experiment is performed under these conditions, which the starting concentration of the fluorine is 0.002 mole per dm cubed. Draw a line on the gradient at figure 1.1 to show the concentration of fluorine and how it changes over the first 12 seconds of the reaction. Now, what it has told you is that, again, its half-life is 4 seconds at this point. So 12 second implies that there are going to be at least 3 half-lives that occur. So we're starting off with 0.002. At exactly 4 seconds, we would end up with a value here. At exactly 8 seconds, we'd end up with a value here. And then finally at 12 seconds, we would end up with a value approximately here. This is what our graph is going to look like. And we started off initially with a concentration there. And then your objective is to simply draw a line doesn't have to be perfect, but a line of best fit through your graph. Now, because it's curved, you're not going to see a perfect line coming all the way through. You won't see a drawn line that's straight. Now, had it said draw a line of straight line of best fit, then you would have had to draw it out with a ruler. But here you can show the actual line curving depending on what they've asked you and from the point of data. Okay. Now, I want you to use your graph in figure 1.1 to find the rate of the reaction when the concentration of fluorine is 0.001. So at this particular point. Now, it is important here, now all of a sudden, to be specific. There's a concentration of 0.0010. We're going to draw a tangent to our line, right? Just make it as perfect of a tangent as it can be. Now, what I generally do is I extend the tangent out to the point where I actually see it hitting certain points on my axis itself. So there's my rise, there's my run. I'm going to use specifically these 2 points, right, to determine, and the reason why it's better that I use these particular types of points, it's a lot easier to address what you're looking at when you know exactly where and precisely what point you're seeing the lines intersect. So I've got 5.4 looks like here is where it ends. 2.6 is where it starts in terms of the x-axis. And then I've got 0.0012 minus 0.0008. So rise over run. Take the difference in your concentration over the difference in your times. And when we solve this particular value out, Now, for example, I end up getting 9.14 times 10 to the negative 4 as my rate. Now, in the mark scheme, what it's done is it's told you that the rate can be anywhere from, again, the range of tangent drawn at 0.001, done. Second, let me check one other thing if I could. Yeah, so I'm getting the same value. No, sorry, I'm getting this value. The one mistake that I've made is I've done the opposite of what I should have here. This should have been, again, the final value minus the initial value. And the value that you end up getting in turn is 1.428. We'll make it 1.43 times 10 to the negative 4. So this ends up being my calculated rate using the understanding. Any questions in regards to this idea? Yes or no? All right. Again, some of you are messaging that you've done these two particular past papers, and that's perfectly fine with us. It's not here to make you do these particular past papers. I've just taken odd questions that I want you to look at in terms of understanding. Some of you had trouble understanding certain odd points. That's all we want to do. I understand this part is probably not the more difficult part for the vast majority of you. You're more than capable of solving these kinds of things out. I wanted specifically to focus in on the mechanism part, and I wanted specifically to focus in on the expression when the overall order is first order, what and how you find the value of k. So you are more than welcome to follow along where you want. If there's certain parts that are not important, again, it's up to you, right? Part A, define KW mathematically by completing the expression. The expression here obviously should always be KW is equal to the concentration of H plus into the concentration of OH minus. I think I'd probably be better served if on doing this, it'll be more legible that way. That would be your KW expression. Now, keeping this in mind, let's move on to part B. It says two solutions, V and W, are described. It says V is hydrochloric acid, HCl, strong acid. W is sodium hydroxide, strong base. The concentration of hydrochloric acid in V is the same as the concentration of sodium hydroxide in W, meaning that the amounts are exactly equivalent in terms of their mole per unit volume content. And then the pH values of V and W differ by exactly 11 at 298 Kelvin. Given this information, they want us to calculate the concentration of HCl in, again, V. Now, here's the way that we have to go about doing this. There's a couple of things that they told you right off the bat that, again, are bits of information that will make it somewhat easier for you to decipher what the pH values happen to be. See, part one, the biggest problem with part one is that it requires you to solve the concentration, right? Or the pH of that particular solution, V, before you can go about determining the concentration. Because whatever concentration of H plus there is a concentration of HCl, and that's dependent on, again, as we said, the pH of your solution. So the way that we want you to remember it is in this regard. Go back to the screen. Sorry about that. So here's what we're looking at. Acid concentration should be equal to your base concentration. This is what they've asked us to remember. Now, having said that, let's say that if I took negative log of the acid concentration. And at the same time, I took the negative log of my base concentration. Remember, what this does is the negative log of the acid concentration is my pH, and the negative log, or if you will, the negative log of my base would become, again, the overall pOH of my given solution, right? That's what this is going to be able to get in terms of my understanding across. So here's what we do know, that when I take the pH of any given solution at a given temperature, and I add that to the pOH of a solution, even though technically this is not a calculation that they would want you to do, this is supposed to be equivalent to 14. Now, having said that, having told you that pH plus the pOH is equal to 14 at any given point in time, at any given temperature of an acid and an alkali that are mixed together, if that is the case, what they've told you is that the pH values of V and W differ by exactly 11. So that means that if I were to take 14, or I took the difference of the pH values, so for example, for whatever the acid is, the pH is this, right? The larger one would be this, by the way. 14 minus pH, this would give me the pOH, minus the pH, should be equal to 11. And what we can do then is to make the pH my X value, and we can solve accordingly. And when we do this, and when we actually solve it out accordingly, so here's what we got. Let me do it again. Sorry. This is the understanding that we want. All right. So you will end up getting the idea here of 2 pH. Sorry, I've written it out here in terms of working out. Here we are. This is what it will become, because log base is pOH, which is 14 minus pH, right? And so what we end up basically determining next is that, all right, if pH represents, again, the pH of your particular solution, then it would be, again, the pH of your base, which is 14 minus pH, minus pH, meaning that of the acid, is equal to 11. The difference of the larger minus the smaller is equivalent to a sum of 11. And when you solve this out, what you end up getting is this expression. You get 2 pH is equal to 3, or simply your pH is equal to 1.5. So now you know that if the concentration of hydrochloric acid and sodium hydroxide in a mixture are exactly equivalent, the pH of the hydrochloric acid should be 1.5, and the pH therefore of, again, your actual alkali would be 1.5 plus 11, or 12 and a half. So these would be the pH of your two resultant solutions at this particular point, right? You would get 15 and 1.5 respectfully. Now, once you've done this part, the next part is pretty self-explanatory. Your H plus ion concentration is equal to 10 raised to your negative pH, so negative 1.5, and that in turn will give you a value of exactly 0.0316. This is the concentration of your H plus ions when, again, in this situation, you have a pH of 1.5 and 12 and a half. Now, equal volumes of two solutions, V and W, are mixed, giving solution X. Name solution X and state its particular pH, right? If I give you equal amounts of this monoprotic acid and this single base, then remember the solution X that they're talking about is basically your salt solution, NaCl, right? Aqueous sodium chloride is what you would get, and the pH of that resultant solution, if you're going to add equal amounts of both the acid and the base, would neutralize each other to give you a pH of exactly 7. Now, the next part says that if a 1 centimeter cube sample of 1 mole per dm cube nitric acid is added to 100 centimeters cubed of solution X forming mixture Y, and then in a 1 centimeter cube sample, you're adding 1 mole per dm cube KOH to 100 centimeters cubed of solution X forming a mixture Z, they would want to know what your pH values would end up becoming then. Now, in terms of understanding, here's what you've done. You've basically added 1 centimeter cubed of increasing the concentration to 1 mole per dm cubed, right? You started off with 0.0316 as the original concentration of the hydrochloric acid. You've added, again, a 1 centimeter cube sample of a concentration of 1 mole per dm cubed. So basically, you've added, if you look at it, exactly a precise amount into that volume. Because you've increased the amount of H plus ions to a small degree, not a very large degree, you will then take your actual pH from so here's what we want. We started off with 1.5 for our actual acidic solution. You have 100 centimeters cubed of this, right? You've been given a 1 centimeter cubed sample of 1 mole per dm cube. So one way of doing it would be to determine exactly the amount of H plus that is present in your overall solution. So if you look at this, you've got from the nitric acid, you've got 0.001 moles of your H plus ion concentration being mixed in with the 100 centimeters cubed of the original solution, which was so now you get 0.00416 moles of your H plus. If I divide this by the volume of solution, which would be 101 centimeters cubed, I get a concentration of 0.0411. And if I take the negative log of 0.0411, I will end up getting 1.38. So my pH will become 1.4. They've given you the answer anywhere from 1 to 3 is sufficient, right? And if I increase this, or if I've gone from what was initially 1.5, right, to 1.4, I've decreased the pH from 1.5 to 1.4, then I'm going to go ahead and increase the pH of the other one by exactly the same amount. 12.6. I mean, simple way of doing it. Simply took the amount of H plus that were present, added up the total amount of H plus ions that are there from both strong acid solutions, and then divided by the total volume. That gave me the pH of the resultant solution, and whatever decrease I saw in the pH of the strong acid, utni hi increase beta I made onto the pH of the strong base. Okay? Now, given this next part says CH3, CH2, COOH, and you've got basically propanoic acid, and then you've got two dichloro, two dichloro propanoic acid, and then you've got sulfuric acid. All of them happen to be acidic in nature. And what it wants you to do is it wants you to decipher, right, of these, what would be the order of their, again, acidity and an explanation. Now, here's the thing that we want you to specifically focus in on. The first part, obviously, the easiest part of the answer is that you start with H2SO4. And then the next one that should follow through should be the CH3, CCl2, COOH. So the 2,2-dichloropropanoic acid. And then the least acidic would be the propanoic acid itself. Now, that's the order. That's contingent on 1 mark. However, more important than this is the explanation that you would go through to describe. So first thing you need to talk about is the fact that sulfuric acid fully dissociates. That's where we want to start first by going ahead and mentioning the ideas to them in a very specific manner. Once you've talked about the fact that it fully dissociates, that's sufficient for the sulfuric acid part. Now, then we start talking about, again, the other 2 acids. Both are weak, by the way. Now, we've talked about this point, and these are the things that you've got to put in your head. It's got to be about, again, the stability of the anion that would be left behind when the proton is broken, which in turn is what causes or allows the proton bond to easily break apart, that OH bond in the carboxyl. So you've got to mention a couple of things here. So when we talk about, again, the CH3, CCl2, COOH, again, remember, has an electronegative atom, which stabilizes the delocalization, of the carboxylate ion. Making it easier to deprotonate. All right, so that's the second part. Note, the key of what I wanted to kind of put together is I'm mentioning the idea of the deprotonation. That's the priority. That the fact that you now have those 2 chlorines present near the actual carboxyl, the actual delocalization becomes more stable, making it easier for you to lose a proton in the first place. However, in terms of the propanoic acid, that is the idea that we're looking at here, right? Because you've got those alkyl groups, remember they're electron donating, they have positive induction. What they do is they basically disrupt the delocalization of your carboxylate, making it more difficult for the deprotonation to occur. The more alkyl groups you have, the less stable the delocalization will become, the less likely the deprotonation will be. The more electronegative atoms that you see, and the closer they are to the carboxyl, the more stabilized the delocalization of the carboxyl it will be, and the easier to deprotonate your H plus will become. Okay? That's the understanding you want to keep in mind here. Now, mentioning out all of these conjugate bases is pretty straightforward stuff. Like, for example, if I were to take H2SO4 and put it into water, there is a bunch of possible conjugate acids and bases I would get. One of those that we need to talk about right off the bat is our H3O plus and our H2O, where the water would act as our base and its ability to accept the proton will turn it into H3O plus. The other ones that you want to look at are going to be this one, all right, H2SO4 is one acid. Its conjugate base ends up being HSO4 minus. And then finally, the last one is the HSO4 minus, acting as an acid for exactly this conjugate base, the sulfate ion, the SO4 2 minus. So this is what we would end up seeing. This is how we would end up getting our actual conjugate acids and bases. The key between all three is that the difference between their formulas should be H plus. That's it. Now, the partition coefficient idea. Now, the only reason I've hit this is that it somehow seems to be substances that we tend to forget or ideas that we tend to forget. It doesn't, it appears every year, but it's something that you should be very clear in terms of what you're doing with. So the partition coefficient, the KPC in specific, here's the understanding that we want. It is the ratio of the concentration of a solute partitioned between two immiscible solvents at equilibrium. That's the understanding that we want you to have. That you've got this equilibrium between these two immiscible solvents that's been created by putting one common solvent between them. That's the understanding that you should take. All right, so you've been given 5 grams of Q, which is shaken with a mixture of, again, 100 centimeters cubed of water and 100 centimeters cubed of hexane at 298 Kelvin, and left there, and until left there's no further change in the concentrations. They told us at 298 Kelvin, the KPC was 7.84, right? So we want to determine what that particular value would be. Now, given that the volume is the same for both solvents, the volume will cancel out. The way that we would go about solving said expression would be this. We know that you started off with 5 grams that were present initially in water. So according to your KPC, which again is 78.4, you would take 5 minus X as the amount of solid that would be present in, again, inside of your particular, you started off with 5, X is what has been decreased. You divide that by, again, the value of X here, which would be the amount of solvent that would be left over in the aqueous solution. So the amount in the organic, 5 minus X, divided by the amount that would be left in the aqueous, which is X. All of that is equal to 78.4. And then you simply solve out for the value of, again, X, which will give you That is the amount of, again, your substance that is dissolved within water. Okay? That's the understanding. Now, it says that part three, a sample of Q is then shaken, which whatever this substance is, Q is then shaken with a different mixture of water and hexane and left until there is no further change in the concentrations. It is found that the mass of Q dissolved in each solvent is exactly the same. All right. Use a KPC value to suggest possible values for the volume of water used and the volume of hexane used. So look at what they've said a little bit earlier to you. They said that, again, in this particular expression, you got, or 7.84 and overshot here. What is this saying? It's saying that when you dissolve the substance in the solvent, in the organic solvent, it's 7.84 times greater in solubility than it is within the water itself. So that means that if I want to dissolve the same amount of the solute, the volume of your water should be literally 7.84 times greater than it would be for, again, any particular volume where the same mass of hexane would dissolve in the organic substance. That's what this means, that it's 7.84 times more soluble in the organic solvent than it is in water. That's what they're trying to tell you when they give you the KPC. So if that's the case, then if we want the value of mass to be equal, then that means that, again, the volume of your water should be 7.84 times greater than the volume of your organic substance. So let's say that if I decided to take 10 centimeters cubed of my organic substance, right? In that scenario, the volume of water would need to be 78.4. Then and only then could I possibly dissolve the same mass of solute for this particular, again, amount of solvents. Now, if I wanted to double, if I went from 10 to 20, then I would have to show accordingly what the volume of water would be as well. Now, the other thing that we want to be clear about is this is the understanding here. Now, let's say that some of you noted that said they've already given us 100 of each, right? So, or they're given us a total volume of 200. What if we need to, again, remember that we're getting a volume that's going to be equivalent to about 200 centimeters cubed? If that's the case, then you can also go with this. Right? This would give you that particular ratio again of what was supposed to be 7.84 times greater given, but now the volume is out of 200 centimeters cubed. All right, it says Q is more soluble in hexane than it is in water. I think that's pretty clear with in terms of the understanding that they've given, right? It is suggested that Q is either one of KCl or a fairly long alcohol or methanoic acid. All right, it wants to know of these, what would Q be, and explain your answer. And keeping this in mind, if whatever Q is happens to be less soluble in water and more soluble in hexane, that generally implies that Q is probably non-polar. So out of these three choices, the least polar would be this particular substance. That is the idea that we want. Okay. Now, we're going to speed up a little bit here. I'm not as concerned about most of you having the ability to solve through the entropy and the bond energies and the delta G. I am, however, a little bit concerned, or when I generally ask students, one of the other aspects that they seem to struggle with a lot more than others is this particular type, the reactions that can be determined from electrode ideas. So you've been given two E naught values, right, for two electrode reactions. For the peroxide electrode in acidic solution, it's E naught is plus 1.77. For the chromium to the chromium to chromium 3, again, chromium 2 to chromium 3, it says that it is negative 1.41, right? And what it wants you to do is that an electrochemical cell is constructed using the following. Again, half cells. You've got an acidified solution of peroxide with a platinum wire, Cr2 plus, Cr3 plus, again, a platinum wire. They want you to identify the positive half cell and calculate the standard cell potential. Now, here's what we want you to remember. First things first, whichever one has the more negative E naught value, that's going to end up being your negative electrode because that's the one that will oxidize in preference to the other. So if the Cr2 plus is going to be oxidizing into Cr3 plus, what that specifically means is that that chromium end or the chromium half cell would act as my negative electrode. Now, if that's the case, if the chromium is the negative electrode, the positive half cell is the hydrogen peroxide. And the E naught cell can simply be solved out in one way. The best way to remember how to solve out the E naught cell is to remember this formula. E naught reduction minus E naught oxidation. The reduction is, again, the more positive E naught value. The oxidation is the more negative E naught value. So we're looking at this. And you should get an E naught value of plus 2.18. That is how we would solve this out. Now, the next part is again linking to the delta G formula that comes in when we again talk about our particular E naught values and that delta G formula. So this is one of two delta G formulas that you should be able to write into your exam itself. And that is delta G is equal to N times the E value times your Faraday constant. So your E naught cell times the Faraday constant. This is what your delta G would be. Now, remember that this delta G would be calculated in joules per Kelvin mole. That is one point that you cannot forget. So that way, when you do write the answer at the end to kilojoules per mole, you do it correctly. So they're actually, again, giving a mark for this delta G expression, the way that it is written. And there's a minus here in terms of the N because we want to make the delta G negative as we want to make the E naught cell positive. Remember, delta G is negative for feasible reactions. E naught cell is positive for feasible reactions. This is why you need that negative sign there. So let's go ahead and plug the values that we know. There are, again, 2 moles of electrons that are moving through the circuit. We said that the voltage was 2.8 volts. And we know that for 1 mole of electrons, the amount of electrical charge is 96,500 coulombs. Now, this value will come out to be fairly large. But because we want to solve it out in kilojoules per mole, we're going to divide by 1,000 because, again, the answer you get will be in joules per mole. And you get this numerical value, negative 420.7 kilojoules per mole. All right, that's the idea that we're looking at. F, the E naught values for the 2 electrode reactions again are given this time given cobalt, which is E naught 1.82, which is more positive than the peroxide. You once again got the electrochemical cell, which is constructed in the following half cells. An acidified solution of peroxide under standard conditions of platinum wire, then the half cell of solution containing 0.02 molar cobalt 3 and 2 mole, excuse me, 2 mole per dm cubed platinum wire of cobalt 2. Using all of this, they want you to calculate the E naught, the electrode potential for the half cell using your Nernst equation, right? So your Nernst equation looks like this, obviously. you are going to solve for whatever the E value is by taking your standard E naught value, right? And to this, you're going to add an expression of 0.059, which is equivalent to the energetics, remember, that going into the circuit divided by the, excuse me, the number of electrons that are traveling through your circuit, which is in this case 1, okay? And then you're going to multiply all of this by the log of your oxidized particles, or the concentration of your oxidized particles over the concentration of your reduced. So log of 0.02 divided by 2. This is your Nernst equation. Now, once you've set that Nernst equation up, right, it will give you, and sorry, this should have been 1.82. So when you set all of this up and you solve accordingly using your Nernst equation, your answer should come out to be 1.702 volts positive again. Okay. Now write an equation for the cell reaction that occurs under these conditions. So remember, this time, given what we see here, we want this electrode potential to shift this way. We want this electrode potential to shift this way. We do want the entirety of this to be doubled to make sure that the cell has a balanced number of electrons. So you are going to see this as your set of reagents. All right, and here's the thing, under these conditions, actually, I take that back, I apologize. Look at what we've just done. We've shown under these conditions, the E naught value is now 1.7. So actually, if this E naught value has now become 1.70 volts, this one will oxidize and this one will reduce. Keep that in mind. You have decreased the concentration of the cobalt um, 3 to such a degree that it causes the equilibrium to shift more and more towards a cobalt 3, causing the E naught to become, or the E value to become 1.70. So now you're going to have the oxidation of your cobalt 2 while the reduction of your peroxide into water. So everything that shows up in your respective equations should show up here. And 2 waters. That would be your overall reaction. All right, hydration again is the enthalpy change when 1 mole of any gaseous ions are added to enough water to form an aqueous solution, right? So I believe most of us are familiar with this. Now, looking at the understanding of the Hess's law representation, calculate the and complete and label the energy cycle to show the relationship between the enthalpy change of solution ALF3, right? The lattice energy of ALF3, and the changes of hydration of Al3 plus and F minus. So here's what we're going to do to show the actual overall process, if we could, right? Now, we're starting here, where we're going to have our ALF3 solid added to enough water to cause this to happen. This is what we would end up getting, and this would represent, again, the enthalpy change solution of Al F3. So that's what this arrow would represent. Now, up here, we would have these ideas. Gas here. And here we'd be looking at right the lattice energy of, again, AlF3, while this would be the hydration energy of Al3 plus, and delta H hydration, given a symbol here, and the hydrations of F minus, or 3 times actually. That is what this second one will represent. So this is what, again, the Hess's law cycle would be. Says the solution of AlF3 is negative 209. The hydration of aluminum is negative 4690. The hydration of fluoride is negative 506. They want you to use this to calculate the enthalpy change, lattice energy of aluminum fluoride. So here's what we've got again. Enthalpy change solution should be equal. That's what we want you to start with first. Enthalpy change solution is equal to, again, the summation of enthalpy change hydrations minus the enthalpy change lattice energy. This is our formula. Now, what do we know? We, for example, know the enthalpy change solution of the AlFO3 to be negative 209, which will be equal to the negative 4690, which is, again, the hydration of your aluminum ions, plus 3 times negative 506, which is the hydration of your fluoride ions, minus the enthalpy change of your lattice. And so that's what we're going to be asked to simply plug in. And when we plug the values in here, the answer that they've shown is negative 5999. That will become your lattice energy for aluminum fluoride. All right. Now, I'm not as concerned here about this particular part, more concerned with just the understanding of making you remember certain copper species that are more important than others. So, for example, if we're going to talk about copper, if you'll note, you've got copper nitrate is added to water to form solution A, right? That would be the hexa aqua copper 2, the copper 2 ion surrounded by 6 water molecules in a ligand. Then you add a little bit of ammonia, you get a precipitate. That would be the light blue precipitate of copper 2 hydroxide. Then you add excess ammonia, you get a deep blue solution, and you get again, if you add excess hydrochloric acid, you get a yellow colored solution. So let's start from there. A was, again, this particular complex. This would be the formula of your complex. The color would definitely be blue. All right, moving on to the next one. B, where we've added just a little bit of ammonia. This is generally the considered precipitate for that, copper 2 hydroxide. Again, this time the color of the copper containing substance is light blue. The next one, we've added just enough ammonia to dissolve again the precipitate to give you a deep blue solution. So here's what we would see. You have to show, again, two of your water molecules being swapped out from the original six with two ammonias. And then the last one would simply be this. CuCl4 and the color would be yellow. So you've got to know these four. Can't reiterate this enough. These are definitely the four copper complexes for which you need to know the appearances as they appear. You need to know exactly what the particle is. You need to know exactly what the appearance of the color is. Polydentate ligand, the EDTA, remember polydentate, why? Because it has the capacity of making multiple dative covalent bonds with, again, any particular substance. So that donates more than two lone pairs and makes more than two dative covalent bonds with a central transition metal ion. Now, they've given this understanding here where on the structure, they want you to circle the six atoms that would form bonds with your metal ions. So the six atoms that you need to specify, again, are the four oxygens with the negative charges, because they would have an extra lone pair, and the two nitrogens in the center with their lone pairs that would all be able to make a dative bond with your actual central transition metal ion. The calcium ions, again, and either of these have a coordination number of six. What is a coordination number telling you? It's basically telling you the number of dative bonds that are being formed by, again, the ligand and the metal ions. So in this case, there would be six dative bonds that, again, that your ligands form with your transition metal ion. So that's the general understanding. All right. Now, I want you to focus in on this part two. This is a very easy question if we understand it, but we often end up not understanding it, right? So they've given you several solutions here. Complex of calcium EDTA can be used to remove toxic metals in the body. Shows some numerical values. So the K-stab constants for some metal ions with EDTA 4 minus. So with calcium, it's 5.0 times 10 to the 10. With chromium, it's 2.5 times 10 to the 23rd. With iron, it's 1.3 times 10 to the 25th. With lead, it's 1.1 times 10 to the 18th. Now, an aqueous solution containing this is added to a solution containing equal concentrations of Cr3 plus, Fe3 plus, and Pb2 plus. The resulting mixture is left to reach a state of equilibrium. State the type of reaction where, again, you would undergo this change. Basically, what would happen is that you would end up exchanging ligands. So initially, all of these transition metals, and this led to, they're all surrounded by water molecules. water molecules as their octahedral complexes with six water ligands. And what you would do is then you would have EDTA replace all of those water molecules, thus your ligand exchange. Now, the next part is that, all right, you would get these three particular complexes in your solution. They want to know out of these three, which would have by far the highest concentration and the lowest, and they want you to explain why. So after calcium, the one that has the highest concentration or the highest K stab is the iron complex, meaning this ligand is more likely to occur than any of the others. The higher the K stab, the more likely the ligand happens to occur in nature. So the one that had the highest K stab would be the one in the highest concentration, then would be the next highest, and the least would be the smallest concentration. So if we look at what we've just discussed, you have Fe, UDTA -1. Then you will have your chromium -1. And then finally, at the end, you will have your BBEDTA 2 minus. And the explanation is very simple. The higher the K stab value, the more stable the complex will be. All right. So this is why you would see a higher concentration N, thus lead to a higher concentration present. That's the idea that we want with it. Okay, stoichiometry, not as concerned. I think most of you have the ability to solve those out. This is particularly important. Why? Because it's definitely going to come, right? So if there's any two complexes that show any different colorations, you need to mention two important things. First, that there are different energy gaps between your split d orbitals, first part, and thus different photons or wavelengths of visible light absorbed to promote electrons. Thus different colors seen. This is the difference every single time. It repeats. This question has nothing exorbitantly unique and different about it. You need to mention again the idea of the split d orbitals when you talk about color. You need to mention how, again, you're absorbing energy to go from a lower level to a higher level. And then you need to talk about, again, how different complexes will have different wavelengths of visible light, causing different colors to be seen as different wavelengths are absorbed. 2A, some transition of element complexes can show stereoisomerism. State two types of stereoisomerism shown by transition element complexes. So the first type is geometric, right, or cis-trans. Now, in terms of geometric or cis-trans, you need to keep one thing in mind. This is only going to be true for square planar or octahedral complexes. And even in the octahedral and the square planar, you will need at least two different types of ligands involved. Otherwise, this doesn't occur. The other one are what we call optical isomers or enantiomers, and this will only be True for octahedral complexes with at least one bidentate ligand. So you won't see it with those things like CuH2O6 or any of those particular types. You have to have a bidentate ligand for optical isomerism to occur, right? So you've got a complex here of platinum, which has two ammonias and chlorines, and then another one that has two diethylamines that have the same geometry around the metal ion. Again, the one that has two different isomers can exist as two isomers, whereas the other one only has one possible structure. The geometry that they're talking about is square planar. The way that I know that it's square planar, you've got four ligands around the platinum ion on the other one. You've got two bidentate ligands surrounding the same platinum ion on the second one. The fact that you need to have two different ligands attached to the central transition metal ion at least to form cis trans is where we get the understanding to where it has to be square planar and why you wouldn't see any cis trans isomers when you have the platinum with the bidentate ligand. All right, then you've got this complex ion of CrEn32 plus exists as two stereoisomers as well, whereas a complex exists as the one with CrOCH2, CH2, NH2 3 minus exists as four stereoisomers. They've asked you to complete the three-dimensional diagrams in figure 2.1 to show the four stereoisomers when you would use the ON complex. So let's talk about that. How would we get four possible stereoisomers? All right, one possibility is this. So on the other end, you would get its exact mirror image. That's one possibility. Now the other one would look like this. Right, that's one. And then its exact mirror image would be the other. So what you can see is what I've basically done is in one, I've kept the actual orientation of the oxygens and nitrogens around the chromium in an alternating manner and shown two mirror images of the same structure, or actually, I haven't shown two mirror images of the same structure. I've shown the exact same molecule. Don't do that, please. This is what it would be. And then what I've done with the second one is again shown two mirror images, but this time I've flipped around or oriented the oxygens and the nitrogens in a manner to where they're not in an alternating manner, where they're not alternating to one another. This is how we would end up getting our possible ligands. In this, you will get the cis and the trans idea because in some of them you've got oxygens that are opposite to one another, and other ones you don't have that same consequence. So this is what they're referring to. For example, this or these are your trans options down here. These are your cis. Because if you look very carefully right there, that's how they're creating the trans. Okay? All right, the complex is formed by reacting chromium with a conjugate base of 2-aminoethanol. The synthesis of 2-aminoethanol is shown in figure 2.2. So they've got this molecule called oxirane that they react with ammonia will give you 2-aminoethanol as a result. All right. Suggests a step of the mechanism of step one of the reaction of oxirane with ammonia in figure 9.2. You are to include all relevant early arrows, lone pairs of electrons, and charges and partial charges. Now, remember, basically, what's causing all of this is the ammonia coming onto the molecule on the end that is opposite of one of the carbons attached to the OH, right? And this in turn causes the bond between the oxygen and the carbon to break as well. Now, here's what we want you to have in mind when we draw this particular understanding out. The reason I picked this one is because it's a funky mechanism. It's not one that we're particularly familiar with. Partial negative, partial positive, right? There it is. You're going to have, again, the lone pair of the ammonia attack that carbon, which in turn will cause this particular carbon to have that bond heterolytically broken, leaving the lone pair onto, again, your negatively charged oxygen. So you would end up getting this as a result. That's your intermediate. You can see right now, again, that there's an extra proton here on the nitrogen, and there is one missing there. So this is what basically would end up happening next, just so we're clear. You would have one of the hydrogens break its bond with the nitrogen, leaving an H plus over, right? And that H plus would then travel in this mixture to eventually be attacked by the O minus. That's how you would get the NH2 and the OH. Now, you didn't have to show the blue mechanism in the intermediate. You just needed to show the formula of the intermediate that would form. And then you needed to show how nucleophilically the ammonia attacked one of those partial positive carbons, creating this structure as a result. Okay? So just kind of showing how this is causing nucleophilic addition to take place in this particular mechanism. It's not one that you've seen. It's not one that you've consistently had anywhere repeat in your working. It's just something I want you to understand that you should be familiar with. Okay. All right. A small amount of product E shown in figure 2.4 is produced during the reaction shown in figure 4.2.2. Suggests how this particular process would occur. The only way that that's possible is you had an excess amount of ammonia. Because what would end up happening is instead of, again, the NH2 causing the process, you would have the actual weird looking compound lead to this formation, and you would have, think about your amines. How were they formed, if you remember and recall? They formed due to ammonia constantly attacking the halogen alkane, creating one primary amine. Now, if you had excess amounts of ammonia present, then you could have multiple of those amines attacking more hydrocarbons, attaching more alkyl chains to the structure. That's exactly what's happened here. Here, instead of just having the ammonia attack one end, so you would end up having this molecule form already. And then because there would either be an excess amount of ammonia present or a limited amount of, again, the other substance, the oxirane present, you would have this thing with its lone pair attack yet another oxirane molecule, causing the formation of what you see there. Again, excess ammonia is one possible option, or limited. I think the other name is oxirane. All right, so that's the understanding that we want here. All right, the next part, it says compound F, which is C4H9NO, can be formed through the reaction of the byproduct of C4H11NO2 with concentrated sulfuric acid. It says that compound F is saturated and a basic organic compound, meaning it has to have an amine group, right? NH somewhere. So suggested structure for compound F, state the type of reaction undergone by E to F to form. It's undergone by E to form F in the first place. So here's your E, C4H11NO2, right? Um, and then at the end, you're getting C4H9NO, which is the product, which is a basic product. So we want this to be there somewhere, right? So that decreases, again, the number of hydrogens to be 8. So you've got to have your 4 carbons. Put them like this, because this way, again, each of your carbons, that's 4 point CH2s, and put an oxygen in the middle. That's the only way that the combination will cause, again, to first have your basic group here, still be present, and then have two hydrogens per carbon for the rest of the structure. The type of reaction that they're looking at specifically to make this occur is that from each of your particular molecules, if you look, you're losing two hydrogens and one oxygen. You're losing water. So anytime that you lose water, you undergo a dehydration. So you didn't need to know the mechanism in particular. You just needed to understand that if water is leaving, then this is most definitely a dehydration. Okay. Now, not as concerned about this particular part, but I think we can just kind of mention the idea. The relative basicities of ethanamide, diethylamine, and ethylamine in aqueous solution itself, right? And it wants you to be able to tell them which one ought to go where. Now, the most basic of these particular molecules will be the diethylamine. Then will come your ethylamine. And the least will become your ethanamide. Now, that's one mark. The second, third, and fourth will be dependent on your ability to realize that, again, basic properties are linked to the ability of your nitrogen, your lone pair on the nitrogen, to be able to accept a proton. So we need to mention right? So this is the understanding that we need to have in our head. That idea is going to be important that you get portrayed across. Now, why are the ethylamines, the diethylamine, the ethylamine? So the ethyl groups or the alkyl groups attached to the amine cause the lone pair to be enhanced by the positive induction of the same alkyl groups, making it easier to accept a proton, right? We want that idea here. So this is why the two ethylamines are going to be more, if you will, basic than your actual ethanamide. And then in the ethanamide, you need to mention your actual C double bond O extends its delocalization onto the lone pair of the nitrogen that it's attached to in the amine group in the amide linkage, making it less likely to accept a proton. Okay, buffer solution, just be very careful here. It's not that most students don't know what a buffer is. Just be careful that they want you to tell them that, again, it resists change in pH. Most students remember that part, but you need to be able to be specific when only a small amount of acid or alkali is added. So that's the second one. So again, resist pH when a small amount of acid or alkali is added. The ability to use alanine, which is one of the substances, the amino acid that they've given up there, as again an actual buffer. They want you to write two equations. Basically, it's the ability to convert both sides of the same molecule, the same alanine molecule, to react with either the proton or the OH minus ions. For example, we're talking about this. This is my alanine structure. Let's say that I take this alanine structure and I react it with H plus ions. This part of the molecule, the basic part of the molecule, will immediately attach the proton onto its structure and use up the H plus. So there's no longer H plus, pH can't go any further down. Taking the same amino acid, with OH minus, here's what you would see this time. Your carboxyl will give up its proton, leading to the formation of a carboxylate and a proton at the end. Again, another one is glutamic acid can also be used as a buffer solution. They wanted here for you to show, again, the skeletal formula. So the way that you ought to do this is simply count up the number of carbons that are attached together. That's what you would get. You can see on the second carbon, right? On the first, on one end, you have a carboxylate, and then on the other, you also have a carboxylate. And then either way, from left to right or right to left, you can put on that second carbon right here, your amine group. That would be your skeletal formula, right? Pretty simple, pretty easy, nothing complicated about that. Now, structure for the dipeptide. What is it that they want here? You've given you the alanine, which is the one with CH3CH, and then you got this glutamic acid with multiple carboxyls, and they want you to join them together to show a displayed peptide bond holding alanine next to glutamic acid. So this is your alanine structure again. Now, one other thing I want to be very clear about, this is not a polymer, one molecule of each. The idea of the polymer would be different because they would mention that you have multiple monomers put together. So you would show extension lines. You need to show absolutely zero extension lines here. This should come up at one end. Then you should have your CH with a CH3 and an H here. Then, Rita, you will show your C double bond O. That's from the carboxyl. Again, you would have your amine. The other one, this is where glutamic acid starts. There's your amide or peptide bond, if you will. Then, once again, you will show your CH. And then you will show everything else that comes up on that glutamic acid, which is CH2, CH2, COOH. And then you can either show it this way or you can draw it out in terms of displayed formula. The key is that you needed to show the peptide with the amide displayed, holding the two amino acids together. Okay? All right. Isoelectric point of alanine is 6.0. Glutamic acid, it says, is 3.2. So a mixture of dipeptide, alanine, glutamic acid, and its two constituent amino acids is analyzed by electrophoresis using a buffer of pH 6.0. So if I'm using a pH of 6.0 where glutamic acid is supposed to be neutral at 3.2, remember what that means is that at 6.0 you've added more base into the mixture. So for glutamic acid, what would end up happening is when you add more base, both of these would end up becoming negatively charged, and there would only be one ammonium present, so the charge would become -1 overall. Now, that being the case, it would cause your normal glutamic acid to also move towards the positive plate, but the mixture to move a little bit less towards the positive plate. The objective of understanding is this. So we are going to see alanine here. You would see the mixture of the two here. And you would see glutamic acid here, right? And this is where you show the relative position points, right? And in terms of your overall explanation, what you want to be specific about, it says draw and label the three spots and indicate the predicted position of each of these three species. Explain your answer, right? So you've gotten 1 mark for the relative idea of where they are. You need to mention that the alanine is neutral at its isoelectric point of pH 6. But remember that the other two glutamic acid, GLU, and GLU ALA are both negative. And then finally, that the GLU ALA has a higher MR than just GLU. That's why, again, it travels a shorter distance towards a positive plate, as does the glutamic acid. Okay? All right. Now, just quickly, let's wrap up with these really, really quickly and get to the organic parts. So alanine, there it is, reacts with methanol to form the ester G under certain conditions. So they've shown how you, again, get the ester formation to be present. You've been given the proton and mass spectrum of G dissolved in D2O. Now, just the moment I see that idea of the D2O, I understand that this would be the proton that would disappear. So if you look very clear onto your spectrum, you should be seeing what basically is the equivalent of 1, 2, 3 sets of proton peaks, nothing else except those three particular proton peaks that are appearing very abundantly clear in terms of your molecule. Now, yes, here we are. So splitting pattern for each of the peaks, 1.4, 3.5, 4.0. And then the number of protons that are adjacent to the carbon, as well as the number of protons responsible for each respective peak. So let's label them out on the structure if we could, to be more precise. On G, we are looking at these three protons here, these three protons here, and then the single proton here. So that's 3 hydrogens here, 1 hydrogen there, 1 hydrogen there. Now, if I could give these numbers to kind of make my life easier. So if you look here, let's call this peak at 1.41. We'll call this 2, and we'll call this 3. If you look at peak number 3, you see a quartet, right? 4 split particles. So just so we're very abundantly clear, that's what we're referring to. Because the adjacent carbon is a CH3, meaning the adjacent carbon has 3 equivalent protons, so that would mean 3 plus 1, you see a quartet, right? Now, this peak right here is representative of that one, and then this peak is represented of that one. So this is how our peaks are going to be represented. Now, looking at where they happen to be, I've got one at 1.4. So if I look at my data, that would be an alkane next to, if I want to be very specific, just an alkane on its own, even though it is next to an ester. All right. And here's my mistake. Let's fix that mistake. This is not, two is not a doublet, it's a singlet. And so we have to go ahead and redefine. This is that one. And this is that one. So the first one, again, the reason why it's only shielding to a little amount, because it's simply an alkane. It falls into that range of the CH3 next to another CH. The one that 3.5 is an alkyl group next to an alkane group next to an electronegative atom. And then the one that we see at 4 is the alkane that is attached directly next to an amine group on one end and a C double bond O on the other. So you've got a CH that is attached to, yeah, same idea. CH2 next to O and a CH2 next to C double bond O, actually. All right, so splitting pattern for 1.4 is that it is a doublet. Now, again, the number of protons that here are present here are 3. That's that CH3 at the top there. Number of protons adjacent on the adjacent carbon was 1. At 3.5, we're seeing a singlet. Again, that singlet is a little bit higher because it is also made up of 3 and there are no adjacent carbons. So there's no protons on any adjacent carbons. The 4.0, now this is a quick question or quick understanding. Why, technically, this one should show similar, if you will, shielding as to the 3.5. The reason why it ends up at 4.0, however, is because it has, again, a C double bond O on one end, and because then it has an amine on the other. So it's actually next to 2 electronegative groups. So a little bit more shielding occurs for that particular reason, and it is a quadruplet, is what we're seeing. And the protons responsible for this one is only 1, and the adjacent carbon next to it has 3 protons of its own. All right, the proton and the described difference observed in the spectrum and the proton NMR and D2O shown. If this had been done in CDCl3, you would have seen again the proton for the NH, the alkylamine. Yeah. In CDCl3, there would be an alkylamine peak. So that is the idea that we want. Okay. Now, not to waste a lot of our time, but let's quickly move on to this next aspect. And I'll probably end up with this last question because I think your benzene kind of structure that you see at the end, you are responsible for. And I think most of you can understand it. I do want you to look at it. I've gotten it from the May-June 2023 chemistry PU paper from Cambridge because simply it's something that they haven't asked a lot of. I'll just quickly recap in the end. What we're doing here just quickly to get this out of our mind and understood. When I get KSP expressions, the first thing that I'm going to do is I'm going to write that KSP expression. So this is my KSP expression, right? That's what it would look like. So if I want the KSP itself, it would look like this: Ag plus squared CO2 2 minus. The unit would be moles to the third over dm minus 9. Now, calculate the equilibrium concentration of Ag plus in a saturated solution. Now, this is always a contested question, not because students don't know what they're doing, but simply because at the end, we've got to be clear what we're looking for. So when I solve for the concentration of Ag plus, you need to understand something first. X will give me the concentration of silver carbonate that dissolves. Now, if I know that X represents the amount of silver carbonate that dissolves, then that would be 2X would be the amount of Ag plus, and X would be the amount of carbonate that would be present because of silver carbonate dissolving in the same solution. So first thing that you've got to remember is that when we do calculate the value of X in the end, that will tell us the amount of silver carbonate that dissolves. But for every one silver carbonate that dissolves, there's two Ag plus ions that are formed. So in the end, we're going to have to multiply that concentration by 2 irregardless. So first thing that we do is, I'm going to show the solvation here. KSP would then be equal to, we said that this was 2x squared. We said that this was x. So all of this is equal to 4x cubed, right? So in order to solve for, again, x, it would be the cube root of your KSP, which is 6.3 times 10 to the negative 12, all divided by 4. This, in turn, will tell you exactly and precisely the concentration of your Ag plus here, or your concentration of the silver carbonate, and that comes out to be 1.16 times 10 to the negative 4. Yeah, there it is. Now, this is telling me, again, the concentration of silver carbonate that is dissolved. But that's not what I want to solve. I want to solve for the concentration of Ag plus, which happens to be precisely twice this value. That's why we multiply by 2 here, and we end up getting 2.33 times 10 to the negative 4 as the concentration of the silver ion. All right. If we want, then we've added silver nitrate in here, basically 0.05 mole per dm cube. This will cause, again, the concentration of the Ag plus ions to now become equivalent to the concentration of silver nitrate, because we don't care about the saturation of the silver carbonate anymore. All of the silver ions are going to come from silver nitrate itself. So we set the question up this way. And then we solve for the missing variable, which is the concentration of the carbonate. It goes even lower than it was before, to negative 2.52 times 10 to the negative 9. Why? Simply because, again, you've added so much silver ions that the equilibrium started to shift to the left, right? You increase the concentration of the silver ions, the equilibrium shifted more to the left, decreasing the amount of carbonate ions inside of the equilibrium. That's why the value has gone down yet even further. All right, we've done the Nernst part, we've done this entropy part, which I believe, again, very carefully that all of you can show. What is it that we want to show here? Again, if it's insoluble at 25 degrees centigrade, it's because your delta G is greater than zero at 25 degrees centigrade. Keep that in mind. That a process or a reaction can only be feasible if, again, your delta G is less than or equal to zero at the given temperature. Also, in this question, don't forget this is a mark. All right, that written alone is a mark. All right, wrapping up with the last couple of things here. Let's talk about our carbon 13 spectra for this weirdly looking molecule that I've given you here. All right, sample of pyruvic acid CH3 C double bond O COOH is analyzed by carbon 13. NMR three peaks are observed. Complete the table by circling the carbon atom responsible for each of your chemical shiftings. So if we talk about the first one, you should be circling this carbon because it's simply an actual alkyl group with a hybridization of sp3 that's causing the shielding that you see there. Then you need to circle the carbon at 163 of the carboxyl, which is sp2 hybridized. That's the kind of shielding that it would form. And then what the one that's stuck in between the carboxyl and the C double bond O, the carbonyl next to the carboxyl is what you want to circle here. And that would be due to the sp2. Okay? So be able to understand those shiftings based on the data provided here additionally. Now, for this kind of data. So if you look very, very carefully once more, we want to look at, again, the alkyl group, the one that was at 27. It would fit somewhere here. It's sp3 hybridized. Then we've got another one here at 163. So according to them, it's the alkyl group that, or the carbon that shows up here, right, in your carboxyl, which is sp2. And then the last one, the one that they said was at 192, can be represented here with two alkyl groups either end and C double bond O. 193 is what we got, C double bond O, and then the sp2. Okay. All right. Proton spectrum for this pyruvic acid, again, CdCl3 and analyzed by proton NMR spectroscopy. So they've given you, again, three separate peaks that you can see. If you look, there are three protons themselves. They want to know which is responsible for what. So you've got a triplet here at about 1.25. That would be this one. We'll call it 1, right? And then you've got, again, a CH2 and a CH3 next to the C double bond O. So this peak right here, the second one is this one. And then this one, the one that's the quartet, is that one. Okay? So those are our peaks. Now the group responsible for each peak, starting at our 1.3, it's your alkane group or your alkyl group. The splitting pattern, again, is a triplet. And the number of protons that are responsible for this peak are 3. Right, the next one the alkyl group next to C double bond O, right? This one is a singlet. And that would also have 3 carbons. Actually, 3 protons responsible for it. The last one right? The other way to write quadruplet, you can write quartet, and the number of protons responsible here are two. Okay? All right. Deuterium D2O, where D is H2, can be used as a solvent in proton NMR spectroscopy. Proton NMR spectrum of alanine and CdCl3 has four peaks. Proton NMR spectrum of alanine and D2O has only two peaks. And the reason for that particular understanding is that, remember, in D2O, both of these particular peaks would disappear. So the only ones that would show up would be this and that. Thus, circle the protons that show peaks in both NMR spectra and in both NMR spectra would be the CH3 and the H at the bottom. In your explanation, you would talk about how, in terms of the amine and the carboxyl, those protons would be swapped out with deuterium atoms, and thus the peaks would disappear. Okay? All right. This was the one that I wanted to just kind of go over really, really quickly. The chlorination of benzene ring follows a similar mechanism as for bromination, but uses Cl2 as a reagent and AlCl3 as a catalyst. You've been asked to draw the mechanism for reaction two, including which is this particular mechanism with chloride, or showing the formation of chlorobenzene, right? Involving the catalyst R is used to represent the rest of the molecule, using curly arrows and show all relevant lone pairs and dipoles. The initial reaction involving the catalyst, this is what I'm talking about. This is something that they haven't done in a while. And unfortunately, because they haven't done this in a while, you guys haven't done this in a while. So I would strongly suggest that we understand what the stages of the mechanism are. That this is what, again, your catalyst does initially, creates the electrophile. Once the electrophile has been created, this mechanism is no more complex than what we expect it to be. That's your intermediate. The next step of your mechanism should show, again, that bond breaking and reforming the benzene ring. And once all of this has happened, remember, you get a byproduct of an H plus. So you need to show how in the next step, the H plus reacts with the AlCl4 minus to reform the AlCl3 and give you your byproduct of HCl. So definitely a substitution. And because we had to do it by creating an electrophile, we call it electrophilic substitution. The same thing will be done with every benzene reaction, regardless of, again, where each ring happens to be. Be familiar with, again, proton, electron donating carbon twos, electron withdrawing, electron donating 2,4 directing, electron withdrawing being 3,5 directing, and that will help to dictate how your mechanism steps should follow. You don't need to memorize any particular mechanisms. You need to just know how a certain mechanism goes, whether it's an indicator formation or a salt formation or a medicine formation. You need to follow the steps that they're showing and how you would create that with all of the stages of reactions that follow through. Okay. Again, these are some odd questions. These are not all of them by any stretch of the imagination. If you've hit 23 well, if you've hit 22 well, if you've hit 21 and 20 well, some of you have gone beyond that, but if you've at least hit these 4 years and you've understood each and every aspect, and if any odd points were pointed out today, you're probably going to be in good shape. Don't be alarmed that the questions are going to be not easy. They're not meant to be. Don't be alarmed that, again, there's certain parts that you don't get. Every year, the objective of the paper is to have certain parts that only a select few students would actually be able to get right. There's a reason why the thresholds fall down into the 60s and sometimes high 50s. There are definitively difficult things that you need to focus on. But if you know your electrophilic substitution mechanism, if you know your benzene reactions, that's going to go to take a good chunk of your process and get it out of the way. If you know your physical chem good, if you know how to find lattice energies using again, Born-Haber cycles, which is a very, very easy process. If you know how to find delta G using entropy changes, and you can equate the idea of feasibility to be delta G less than or equal to zero, that's going to give you an automatic mark. So these are the things that you need to focus in on, because these are the processes that you need to focus in on. If you can hit these aspects of physical chem, what I always tell students is jahan pe score banta hai, where you can score, you have to score. So if you get a Born-Haber cycle question that talks about the same breakdown, has a thermal decomposition aspect, those are questions that you've seen 100 times over. They're in every paper for like the last 7 years. You have to score those marks. Those are questions where, again, your market should be like 90% or above. Benzene aromatic compounds and mechanisms. If you know your mechanisms well, if you know your reactions well, that's a question where you need to score well marks. Proton NMR, carbon 13 NMRs are not overly difficult with the data provided. Those are where you need to score marks, right? I would strongly suggest the transition metal question you should clean up on. Knowing how to draw the structures, the K-stab idea, those are marks that you should score on. If you can hit these 4 or 5 topics, you will automatically be above the threshold already. And then whatever you can do in the difficult questions will only enhance your grade. So what I'm simply going to tell you is this, that if you can get physical chemistry, if you can get transition metal chemistry or inorganic chemistry for A2, and if you can do the benzene reactions and the analytical processes at the end, you're already hitting that 55 to 65 mark in terms of threshold. If you can clean up on those marks, everything else that you do above is simply what we would say excessive cream on top of your already made cake, right? So it's just adding on to your grade and enhancing it. So at least hit these particular topics that you probably have seen every year. Because the reason I mentioned those ones in particular, every year for the last 5 years, there's questions on these topics without exception. So if you can score on those that have repetitively been there and the same answers have repetitively been used, those that are somewhat trickier, you can still get half out of the total amount and end up way above the overall threshold. All right. So keep those ideas in mind. Work hard tonight. Just go over only the concepts of some of the trickier things that you need to look at. And inshallah, I'm sure all of you will do well. But these 4 topics, if you can clean house here, I promise you, you will find your paper much, much easier to get through. All right. All right, everybody. Best of luck tonight and your studying. Best of luck for your preparation. And I hope all of you do well tomorrow. Don't be alarmed by the length of the paper. Don't be alarmed by the difficulty of certain parts of the question. You're not supposed to get 100%. Nobody will, trust me. But where you can clean up on marks, please make sure you get those marks. All right? All right, that's me signing off. Best of luck. Allah Hafiz.